Hey guys, um, I am going to be out for the rest of the week. But with that being said, I do want to try to continue on as closely as possible to our normal lessons. So this week, you guys will be going through and working on our new lesson, but that's not meaning I'm leaving you hanging because this video is to help us kind of go through the notes like I would on any given normal day, like we would in class. So I'm going to go through this. I'm going to give you examples. I'm going to have you guys pause the video to try examples on your own and then go over them with you together. Okay, so I can't stress enough that I know I'm out this week. I know it's going to be tough. But biggest help that you could, the biggest thing that you could do to help myself and to help you guys is to actually watch the videos that I'm posting for you with your sound on, watching them fully through, following along, not just jumping around to like to get the notes down little by little. Because if you're not watching it straight through with the sound on, you're really going to have a hard time following with the new concept, and it's going to be pretty tricky. Okay, when I come back next week, so I will see you guys tomorrow and Friday, or we'll have this class tomorrow and Friday. And then I won't see you Monday, but when we come back on Tuesday, I should be back in person. We'll maybe cover a day of this, just going through and answering whatever questions you may still have. But we're moving on. So it's kind of sink or swim here. You better do what you need to do to try your best with this section and follow along. And then, like I said, we'll review it for a day or so when I get back, but we're moving on after that. Okay? So let's get down to these notes. Okay? This whole chapter is a brand new chapter. There's only I think three or four sections to this chapter, but it's all about systems of equations. So the first thing that I want to do is I want to define a system of linear equations. A system consists of two or more linear equations that use the same two variables. Okay? So we've been working with regular linear equations, right? In the last section that we did right before midterms, we were writing equations, we were graphing equations. Those are all equations. The only difference between that and this is a system is looking at a problem that has two equations and kind of comparing and contrasting them. So an example of a system would be something like x plus 2y equals 7 and 3x minus 2y equals 5. So individually, these are both linear equations, but looking at them together, we consider those to be a system of equations. With a system of equations, we want to figure out what the solution to that system is. So we're going to go through and we're going to be solving these somehow to figure out what the solution is. The solution is always going to be an ordered pair, right? And that looks like something like this, where you have the x and the y value that satisfies each equation in the system. So what that means is when I'm somehow able to figure out a value for x, I can plug that value into the first equation and I can plug that value into the second equation, along with the value I get for y. So if I plug in what I get as my solution for x and y into my top equation, I'd end up getting something like 7 equals 7. And when I took that solution that I got for x and y and I plugged it in my second equation, I would still get something like 5 equals 5. So my solution, x, y, those numbers that I get, should work in both of those equations. There are three different ways to solve systems. The first way that we're going to focus on is by graphing, because it gives us a pretty good idea visually on how we actually, or what our solution is actually representing. Okay? So this example says use the graph to solve the system, then check your solution algebraically. So I want to graph this first equation, and then I'm going to graph my second equation. Now, from the section we've done before this, we know that it's easiest to graph these equations if they are in slope-intercept form, right? So my first goal is to get both of these equations in slope-intercept form into y equals mx plus b, because then it's going to be pretty easy for me to graph that. So my first step, my y is by itself. So my idea is that I want to isolate the y, right? I want to get the y by itself. To do that, my first step would be move the x over by subtracting it. So I get 2y equals, the x becomes negative because I moved it, and I get negative x plus 7. My next step to get y by itself, right, to isolate this y, is to get rid of the 2, and I get rid of that 2 by dividing. So when I divide, this negative x is actually negative 1. I'm going to have negative 1 half x plus 7 divided by 2 is 3.5. I'm going to change it into a decimal to make our lives a little bit easier. Okay, so when I divided this, I got negative 1 half because negative 1 is not divisible by 2. And when I divided 7 by 2, I got this decimal. So my first step is to graph this. I'm going to graph my y-intercept first. So I'm going to go up to 3.5, which means I'm going right between the 3 and the 4. And then I have a slope of negative 1 half, which means I would count down 1, but then I would count to the right 2. And I'm going to keep going across my entire graph, and that's kind of important in this section to continue going across your entire graph, because we need to see where our solution lies, and we don't want to graph something that's too short where I can't necessarily see my solution. So I know it's kind of an ugly line here. Okay, I'm doing the best I can, but this is what we have for my first line. I'm also going to now graph my second line on the same graph here. But same thing, I need to get this equation into slope-intercept form as well, so that I can go through and I can actually graph it easily. So again, isolating my y first, I'm going to take the x, I'm going to move it over. It's positive, so I'm subtracting. So I have negative 2y equals negative 3x plus 5. My next step to isolate my y here, I need to get rid of the negative 2 by dividing it. So from here, a negative over a negative becomes positive. I'm going to keep that as positive 3 halves x. And when I take 5 divided by negative 2, I'm going to put it as a decimal. I'm going to put it as negative 2.5. So I'm going to graph the point, my y-intercept, to negative 2.5. And then with my slope as 3 halves, I'm going to count up 1, 2, 3 to the right 2. And again, I'm not doing anything. I'm not stopping until I reach the very edge of the graph, because I don't want to miss anything. Right? I don't necessarily want to miss where my solution would be. So you guys can see that right now, there's no new information that I've introduced to you, right? Everything is what we did in the last section. We've taken equations like this, and we've made them into slope-intercept equations. And we've taken slope-intercept equations, and then we've graphed them. The only new piece of information that I'm going to give you is right now. Okay? So I graphed my system here. I graphed these two equations by putting them into slope-intercept form. When I need to find the actual solution, my solution is where those lines are intersecting. And I know that my graph looks a little rough because I'm kind of doing it digitally here, but if you were to use a ruler on your paper, you should see that these lines intersect at the point 3, 2. So when you're graphing these lines, where they're intersecting, that is considered to be your solution. Okay, but I'm not done, because it's saying check your solution algebraically. What that means is I'm taking 3 as my x value, and I'm taking 2 as my y value, and I'm going to plug it back into these original equations that were given to me to make sure that they actually work out, right? That this is my solution. And what I mean by that is I'm subbing 3 in for x, I'm subbing 2 in for y. So now I have no more variables. 2 times 2 is 4. 3 plus 4 is 7. So I know that this solution 3, 2 works in my first equation. If I got something like 5 equals 7 or negative 1 equals 7, something that's not equal to itself, that's my hint that I either did something wrong algebraically when I was checking, or I need to go back and double check my graph to make sure that actually is the solution. But because I got 7 equals 7, I know that that solution works in my first equation. In order for it to be a solution to the entire system, it also has to work in this equation as well, right? So I'm going to take 3 as my x value. Again, I'm replacing the y with 2, and I'm going to check to see if I get 5. So 3 times 3 is 9, 2 times 2 is 4, 9 minus 4 will give me 5 equals 5. So this solution works in my first equation that was given to me, and it works in my second equation that was given to me. So this check ensures that I have the correct answer. So for all of these problems, once you get your solution, there's no reason you shouldn't be checking to make sure that your answer is correct, right? You should always check to make sure it's correct. That way you're not doing all this work for no reason. Okay? So let's actually put into words what we had done here. Okay? The first thing that I did was I graphed both equations in the same coordinate plane. And we did this by rewriting each equation in slope-intercept form. Right? Again, that's y equals mx plus b. And really, that's the only form we should be working with when we're solving systems by graphing, because it's the easiest form to graph. Once we graphed both of those equations into the coordinate plane, that's where we then estimated the coordinate of the point of intersection, right? So again, I had said mine was kind of rough looking because it was digital, but you should be able to clearly see exactly where those lines are intersecting one another, right? That's going to be your solution. And once we have that point of intersection between the lines, then we're going to check that coordinate or check the solution algebraically, which is what I did over here in blue, right? That's where I substituted the x and the y values into each of the equations in the original linear system. Okay, so we graph both of them in slope-intercept form, right? In y equals mx plus b. Then we find where those 2 points cross. Then we can check that point where they intersect actually is the solution. Okay, so we're going to do the same thing on this example. I'm going to start with negative x plus y equals negative 7, and my goal is to get this into y equals mx plus b. So I'm trying to isolate the y, which means I have to move the x over, and we do that by adding. So I get y equals x minus 7. There's no other step that I have to take here to get this into slope-intercept form because I'm already in y equals mx plus b. Okay, my first point on my graph would be my y-intercept at negative 7. And then my slope, although it's not written here, my slope is 1, which really means I have a slope of 1 over 1. So I'm going to go up 1 to the right 1. And now you guys can see that I'm going across my entire graph because I want to make sure I'm never going to miss my point of intersection between my two lines, right? If I cut it short right here, what if my intersection ends up being over here? I'm never going to see that. So I'm going across my entire graph here. Okay, so there's my first equation. Okay, my second equation again, I need to take this equation and I need to put this into slope-intercept form. So I have x plus 4y equals negative 8. I want to isolate my y, which means I have to bring the x over, right? Bringing the x over is always my first step. So I have 4y equals negative x minus 8, because again, we subtracted it, so it's negative. If I wanted to isolate the y here, I'd have to get rid of the 4, which means I'm dividing all of these terms by 4. So this negative x, like I said, is like negative 1x. So when you go to divide this, keep this as a fraction, because you always want to keep your slope as a fraction. It tells you how to move up and down. But here, we know that negative 8 divided by 4 is just negative 2. So now I have this equation in slope-intercept form. I'm going to graph that. My y-intercept is at negative 2, and then my slope is negative 1/4. So I go down 1 to the right 4, and you can see right now that's where my point of intersection is, right? Because I just covered one of my red dots. I'm still going to go across the whole graph just so I have a nice, neat line to look at. But again, you guys have already seen that's where our point of intersection will be. Oof. Okay. Again, still kind of rough here, but you guys can get the gist of this. Okay. So my point of intersection happens right here, right? This point, my x value is 4, my y value is negative 3. That would be the solution to my equation, to my system. Okay. Again, I'm not introducing any new information other than figuring out where your lines intersect and then checking it. That's the only new thing that I'm introducing. We've done all of this graphing, all of this rewriting equations, and all of this graphing we have seen before. Okay? I still want to check my solution. I want to check that 4, negative 3 actually is the solution and that I didn't make any mistakes. So I'm going to take my first equation, this negative x plus y equals negative 7. I'm going to plug in the 4 for x, and I'm going to plug in the negative 3 for y, and I'm going to double check, does that give me negative 7? So I'm going to have negative, and then I'm going to plug in my x value, negative 4. Then I'm going to have addition. My y value is negative 3, and negative 4 plus negative 3 does give me negative 7. So I know that that point is a solution for my first equation. I still need to double check that it's a solution to my second equation too. So I'm going to plug in 4 for x. I'm plugging in negative 3 for y, and hopefully all of that equals negative 8. 4 times negative 3 is negative 12. So you can put 4 minus 12, or you can do 4 plus negative 12. Either way, both of those will tell you that negative 8 is equal to negative 8. So because this solution works in both of these equations, this is my solution to this system. Okay. So at this point, I would say pause the video here. Try your next 2 examples on the back under the you try problem. So right here, I want you guys to try number 1 and number 2 on your own. Take your time on them. And when you finish them, then you can unpause the video and I'll walk through this with you. Okay, so go ahead and pause the video and try numbers 1 and 2. Okay, so now that we're back here, on number 1, my equation is negative 5x plus y equals 0 and 5x plus y equals 10. Okay, I want to write both of those equations in slope-intercept form, right? So in this case, if I wanted to isolate my y, I would bring the x over. Since it's negative, I have to add it. And I get y equals, you can write it as y equals 5x, or you can put it as y equals 5x plus 0. Either one of those is okay. If you need the 0 there to remind yourself that's where you're going to have your y-intercept, then keep the 0 there. Okay? But that's where my y-intercept is. It's at 0. My slope is 5, which is also like 5 over 1. So that means I'm going to go up 5 into the right one, or I'm going to go down 5 into the left one. And if I had enough space, I would keep going, but I really don't have much here. So that's my first line. Okay, that's my first equation right here. My second equation, this one right here, I also need to change into slope-intercept form. And on this one, if I wanted to isolate the y, I'd have to subtract the 5x, and I'd get y equals negative 5x plus 10. Okay, I know that it's not really on the graph here. Your y-intercept is 10, so it goes just above it. But you're still going to follow this slope. So again, if your slope is negative 5, it's really like saying negative 5 over 1. So you're going to go down 5, and then you're going to go to the right one. And you guys can see right now that you already have your point of intersection. So if you want, you can still go across the graph here, but you have that point of intersection between your two lines. Okay? So my point of intersection here happens where x is equal to 1, I'll write it over here, where x is equal to 1 and y is equal to 5. That's the solution to my system, but I'm still checking. I still need to make sure that's actually correct. So I'm going to take negative 5x plus y equals 0. I'm going to plug in 1 for x and 5 for y. I'm going to take 5x plus y equals 10, and again, I'm going to plug in 1 for x and 5 for y. So with this first equation, I have negative 5 times 1 plus 5. Hopefully that gives me 0. Negative 5 times 1 is negative 5. Negative 5 plus 5 does end up giving me 0. So that works for my first equation. Making sure that it works in the second one, I still plug in the 1 for x and the 5 for y. 5 times 1 is 5, and 5 plus 5 does equal 10. Does equal 10. So again, because my solution works in both of those equations, this will end up being my solution. Okay, 1, 5. Same idea on number 2. Switch back to my colors here. On number 2, I have the equation negative x plus 2y equals 3. If I wanted to get that into slope-intercept form, first thing that I'd need to do would be to add the x. So that gives me 2y equals x plus 3. And again, if you want, you can put this as a 1x, because in this next step, to isolate the y, I have to divide by 2. So I get y equals this 1x divided by 2. I'm going to write it as 1/2 x. And again, you can change 3 divided by 2, because it's not divisible by 2. You can change that to a decimal. You can change that to 1.5. So that's where I'm going to start. I'm going to put my point at 1.5 on my y-axis, excuse me. And then with my slope being 1/2, I'm going to go up 1 and then to the right 2. And again, I'm doing this across the whole graph, so I'm not missing my point of intersection anywhere. Oops. Okay, so here is my line. So that was my first equation. My second equation, this one here, I'm going to take 2x plus y equals 4. I want to isolate the y, so I subtract the 2x, and that gets me right into standard form right away. I'm sorry, slope-intercept form right away. I have negative 2x plus 4. So I'm going to start by making my y-intercept my point right there on 4. And then again, my slope as negative 2 is the same as saying negative 2 over 1. So you can go down 2 to the right 1, and you can see there's my point of intersection there. Okay, and again, I would suggest probably using a ruler on these, just so you have those nice straight lines. You're not missing that point of intersection. Again, I know that mine look kind of rough here. Okay, but you guys can clearly see that's where my lines are going to intersect right here. So that is at the point 1 for x and 2 for y. 1, 2. Okay, I'm going to check that. So I'm taking the original equation. Every time I've taken the original equation, not the new version that I solved for to graph. Right, I'm always checking it back into the original. So I'm going to plug in 1 for x. I have a negative here. I'm going to plug in 1 for x. I'm going to plug in 2 for y. and I'm hoping that this will get me 3. So negative 1 plus 2 times 2 is 4. Negative 1 plus 4 will end up giving me 3. So it works in my first equation. Excuse me. I need to check my second one. So 2 times, I'm plugging in 1 for x, I'm plugging in 2 for y. 2 times 2 is 2. 2 times 1 is 2. 2 plus 2 will give me 4. Right? So I know that it works in the second one. So the most important thing, the only new information that I'm providing you guys is just figuring out what the solution to the system is and just being able to check it. Okay? I can't stress enough, this is not new information. Taking this equation and writing slope-intercept form to graph it is not new. Okay? This is the only new information. So I want to just go back here. I want to look at this word problem. It says the cost to join an art museum is $60. If you are a member, you can take lessons at the museum for $2 each. If you are not a member, lessons cost $6 each. Which system of equations can be used to find the number of X lessons after which the total cost of Y lessons with a membership is the same as the total cost of lessons without a membership? So we're comparing two things. We're comparing people that have a membership, and we're comparing people that do not have a membership. So I'm going to make a little chart. Member and non-member. And I'm going to just use this to organize the information given to me. The cost to join an art museum is $60. That means you're joining it as a member. So you're paying $60 to start with just to become a member. If you're not a member, you're not paying anything up front. You're paying $0 to start with. Okay? If you're a member and you want to take lessons, you're only going to pay $2 per lesson. If you're not a member, meaning you never paid that $60, your lessons cost $6. So we want to write an equation in slope-intercept form that represents being a member of this art museum and being a non-member of this art museum. Okay? So I know I have y equals mx plus b, right? So really, I'm plugging in something for m, and I'm plugging in something for b, right? We know that when we graph our b value, our y-intercept is always our starting point. In this case, this $60 is our starting point, right? That's what I'm paying just to become the member. It's that one-time fee that I never have to pay again, but that's my fee that it costs to become a member. Every time I want to take a lesson, which I don't know how many lessons that we would take, but every time we want to take a lesson, it's $2 per lesson. So think of X being how many lessons you're taking. You're going to pay $2 per lesson. So right now we're looking for y equals 2x plus 60. That means this one and this one are out. I still need to write an equation for the non-member. Okay? Again, I'd have y equals mx plus b. Again, b is our starting point. It's what we would pay that one time, right? But we're not paying anything to start with, right? There's 0 there. There's no starting fee. But we'd still have to pay $6 per lesson. And we had said X is how many lessons or the number of lessons you would take. Okay? So in this case, I have y equals 6x plus 0. That's the same as saying just y equals 6x. That cancels out C. That means D is my only option here. Okay. I'm going to come back to address the homework, but I do want to add something in on the bottom of these notes here that I had not done so already. I want to talk about special cases. Okay. So if we think of these systems of equations, right, and we're trying to find the solution, and the solution is where my lines intersect, we have to think about parallel lines. Because if we have parallel lines never intersect. Right? If they never intersect, and the intersection of lines is the solution to the system, then there's no solution if your lines are parallel. Okay. The intersection is always the solution to the system, but if you have parallel lines that never intersect, then there can't be any solution. There is no solution. And one way that you can tell before you even graph the equations on the coordinate plane, one way you can tell that you have parallel lines is by looking at their slopes, because parallel lines always had the same slope. Okay, so if you go through and you solve the equations for slope-intercept form, and you notice that the m value, the slope on both of those equations, is exactly the same, you don't even have to go graph the equation on the coordinate plane, because automatically you know those lines are parallel, so they're never going to intersect to have that solution. If you didn't remember that and you did graph them anyways, you'll see that they have the same slope. They're never going to end up intersecting. Okay, so just something to remember. In regards to this homework, like I said, I am going to be out the entire week, and I don't have a copy of your textbook at home to post, so I don't need you guys to do this homework, okay? What I do need you to do is I need you to check Google Classroom, because I'm going to post something different for homework there, okay? So just keep in mind you don't have to do this, but there will be another assignment up there for you.